Hello and welcome to this webinar dedicated to bulk solar power generation. In this webinar we will see general features about solar energy, some definitions, then concentrated solar power review, concentrated photovoltaics review, and then some ratios and comparisons. In this slide we see how the solar resource available is much more than we need. To give an example, the Earth receives from solar radiation in 10 days as much energy as the known fossil reserves. Another image, the yellow square in the image, could produce as much energy as required by the entire world. This is the vision of the future on the renewables breakdown, and then we see how for next century definitely due to increase in energy demand, solar power could and should definitely play a major role. This slide shows where concentration technology makes sense. This webinar is dedicated to concentration technologies. It means that we need direct radiation. In other words, no cloudy sky. So basically we see in this slide, but can be seen more clearly in this one. So the most suitable places are Australia, South Africa, North Africa, Middle East, south of Europe, then North America and the deserts of north of Chile, Argentina, and also Brazil. In Mediterranean basin there is then a good solar potential. Then there are some projects and some perspectives for the future to build stronger electricity networks all across the Mediterranean Sea. Solar energy fits well in hot climates because electricity demand is related to air conditioning needs. So the blue line represents the electricity demand, the average electricity demand for Spanish system, and the brown line represents the irradiation. So now we will see some definitions. This slide shows a market share among different technologies. So on the bottom, thin film and silicon for residential and commercial applications, and then concentration photovoltaics for utility scale, and concentration solar power for utility and base load. So this presentation will be focused on utility scale technologies, concentration solar power, which is a thermal process consisting on heating a fluid, generating mechanical power through a thermodynamic cycle, for instance Rankine, Brayton or Stirling, then converting mechanical power into electrical power. Concentration photovoltaics is a photovoltaic process, so first radiation is concentrated on the photovoltaic cell, and then this cell generates directly electrical power. Now we are going to focus on CSP technology. We will see project development issues, and then what about generation costs, market perspectives, and support schemes. So CSP technology overview. We have first of all parabolic troughs. This is the most mature technology, well inside the market. It's in operation from 80s, so several decades experience have been accumulated, giving confidence to this technology. Currently there are many power stations using this technology in Spain and US. The power of these plants ranges from 50 to 300 megawatts. Parabolic dishes using Stirling engine. In Europe there are only pilot plants. The average power of a unit is about 10 kilowatts. This is a modular and scalable technology with added advantages as the operation doesn't need cooling water. Central tower. The first commercial power plant of this type was commissioned in June 2007 in Spain. Its power reaches 10 megawatts. There are about 20 megawatts more in construction and also about 20 megawatts in development phase in Spain. Fresnel technology. There are no plants using this technology in Europe. The operating principle is the same as parabolic troughs. This technology will probably find its application in middle temperature uses such as industrial steam or heating and cooling. Parabolic troughs principle consists on concentrating the direct solar radiation into a receiver. So this collection of solar radiation takes place in the solar field, and then with the hot oil is sent to the power block, and then usually a Rankine cycle is used. So this scheme shows more clearly what's the technology in commercial operation today, which is the heat transfer fluid. So the solar field collects the heat through oil heated up to 400 degrees. Then there is usually storage of melted salts. Then with this hot oil is used to produce superheated steam, which is turbined in a steam turbine generating mechanical power and then electrical power. We can see the condenser. The condenser is an important feature, as if we use wet technology, we will consume water, but condenser can also work with ambient air. In this case, the efficiency of the cycle is lower, but couldn't need a huge amount of water for cooling. There is another technology still in the laboratories, which is direct steam generation. So steam is generated directly in the solar field, so there is no need for heat exchange, and then costs are reduced and efficiency is increased. This is coming soon. So now we will see project development issues. We start with site issues. First of all, we need direct solar radiation, so at least 1,800 kilowatt hours per square meter per year, and a measurement campaign is required. We need access to electricity grid and also to gas grid. To electricity grid because there is a big impact of building a dedicated electrical line to reach the main grid. And also gas grid because a fuel is required to maintain temperatures during the night. Then if there is no access to gas grid, other fuels can be considered. There is need to access to water, but this might be a problem, as in sunny places there is a strong competition for water use. So there is a possibility to cool the condenser with ambient air. In this case, there is no need for huge quantities of water, but efficiency of the cycle is much lower. The land must be flat and must be available, so no special interest zones like urban, industrial, environmental protection or any other. And the land should be very flat for parabolic trough technology. The local authorities finally should accept and support the project. This is typical configurations for parabolic trough technology. So basically oriented north-south and then doing the tracking system on west-east direction, east-west. Administrative issues. So we can say how the maturing period of the project is 18 months from a request for administrative authorization to construction permits, going across environmental impact analysis, public information, consultations to affected entities, request for project approval. Then, after the maturing period, there is the execution period, which is more or less 2 years. So, from preliminary basic engineering, purchasing the equipments, supply of equipments, construction, and commissioning and test period. So, the total project period is higher than 3 years. Grid access is a big issue too. So we provide an example here for a Spanish system. First of all, it's needed a warranty of 20 euros per kilowatt. There is a concept of dispatchability which will be developed afterwards. So it needs a request for recognition of this dispatchability. There is a request for access to the grid. TSO provides the conditions for grid access. Then the project developer presents its project, asks for connection point, and then TSO finally provides connection point. What's dispatchability in the Spanish system? The transmission system operator provides special conditions for plants that can be dispatchable. But to be recognized as dispatchable, there are several conditions. First, installation should be controlled from a dedicated TSO dispatching center. This dispatching center is dedicated to renewables. Program should be reliable, and the rate of reliability is needed 90% at 24 hours horizon and 95% at 6 hours horizon. These plants should have a storage ability of 4 hours. This storage ability will be done available for TSO use. The required energy restitution efficiency is 60%. And finally, these plants should be resistant to voltage dip. So the voltage dip right through ability should be higher, should be up to 1 second. Then project developer gets some benefits when the power plant is declared as dispatchable. So there is less requirements and more warranties to obtain grid access. He can also participate in ancillary services market, so getting a supplementary remuneration. So project developer can make the choice to go for storage or not, so making its installation dispatchable or not. But if not dispatchable, grid access seems much more difficult to obtain. So concerning still project development, there are some technological issues. So first, mirrors. Some companies dedicated to solar projects are developing its own technology or buying mirror manufacturers. Absorber tube. This is the most critical element. This is a very technical product, as the vacuum has to be lasting, the layers has to be stable. It's needed high transmissivity of glass, high absorptivity, and low emissivity of absorber. There are junctions, metal glass. There is a problem with dilatations. So currently there is a manufacturer's oligopoly. Support the structure. There are several structures available in the market, basically two streams, US and Europe. There is a continuous evolution to comply with alignment requirements and at the lower costs. Then thermal storage, which is a big issue. Liquid salts is the technology used for the moment, but many other are in development. This image shows how storage optimization is big calculations and big technical economical optimization. Contractual structure and project finance. The basic contracts in this technology are the EPC, engineering, procurement and construction, the operation and maintenance, grid connection and fuel procurement. So the engineering, procurement and construction can be turnkey contract or separated packages negotiated by the project developer. The turnkey contract, in this kind of contract, we find one main contractor that assumes the whole project and outsources the various packages to other companies. The price is negotiated ex ante and is firm, as well as deadline, otherwise there will be some penalties. The responsibility, there will be only one visible head, which is the main contractor. So this kind of contract is as an average 20% more expensive than the option separated packages negotiated by project developer. But to be financed by banks, it's the only contract structure acceptable. The financing entity will obtain from main contractor the required guarantees. So the contractual structure when there is project finance is as follows. So project developer agrees with turnkey main contractor the construction of the project. Then financial entity has a hand on project developer, but has the main guarantees from turnkey contractor. So turnkey contractor has to be a solid institution, being able to offer guarantees to financial entity. The financial entity will check insurances, environmental issues, legal issues, and technical issues. The main risks seen by financial entities are storage, availability of main components, for instance mirrors or absorber tubes, experience and solidity of main contractor. This is definitely a very important point. Expected generation, so what about the availability and quality of solar radiation data? What about the thermal storage, hybridizing with natural gas or biomass? And then they will check what's the regulatory risk, and this is subsidized technology, and then what's the risk of losing these subsidies or encountering some changes in regulatory streams. So some ratios. For a 50 megawatt plant without storage and with storage, investment without storage is about 3 euros per watt. With the storage can be increased by 1.5, 2 or even more euros per watt. The annual production for South Spain, to give an example, is about 2,000 hours. With the storage can be increased to 3 or even 4,000 hours. Water consumption is still quite high, so 6 cubic meters per megawatt hour. This is wet technology, so water is used to cool the condenser, and then usually with wet cooling towers, so based on water evaporation. There is also, as we showed before, a possibility for dry cooling, but with lower performances. There is also gas consumption to keep to maintain temperatures during the night, and collecting surface is about 300,000 square meters, in other terms 52 linear kilometers, without storage. With storage it's increased accordingly, but usually ranges 90 kilometers. Now we will see which are the current support schemes in different places. In Spain, there is a scheme based on feed-in tariffs, so they have provided good confidence to carry out huge investments. So basically, there is a target of 500 megawatts by 2010. This target will definitely be increased in the coming years. There are many projects on the tube. The tariff is market price plus 262 euros per megawatt hour. This lasts for 25 years. After this period, there is still a subsidy of 210 euros per megawatt hour. In North Africa, it's more based on coal to bid from national electricity agencies. It's quite usual to find integrated solar combined cycle. So this is a combined cycle that takes some solar radiation. Then this is definitely a good idea to recover solar energy and optimize the thermodynamic efficiency thanks to high temperatures reached by burning natural gas in a gas turbine. So, to give an example, there are some ISCC by Abengoa Solar in Morocco, 470 megawatts, or Algeria, 150 megawatts. In USA, there is more complex system. There are state requirements, RPS, Renewable Portfolio Standards, also power purchase agreements and federal investment tax credit. So the addition of all these provide the interest to develop renewable energy projects. So in US we find the SEX series from 80s, which is more than 300 megawatts with 20 years experience on parabolic trough technology. But on more currently basis, we find in February an agreement between Arizona Public Service and Abengoa Solar to build a 280 megawatt solar power plant And in April, Pacific Gas and Electric subscribed a firm contract to buy electricity generated from solar plants in Mojave Desert, 500 megawatts plus optional 400 megawatts. What about the market, the current growth? So only in Spain there will be confirmed firmly more than 1,000 megawatts during 2008, and there are requests for roughly 5,000 megawatts. The market expectations some years ago, according to German Aerospace Center, was something like 40 gigawatts by 2030. Today, more updated expectations from Stella, which is the European Solar Thermal Electricity Association, they see room for 60 gigawatts by 2030 only in Europe. Well, this is maybe optimistic expectation, but it shows how this technology is evolving very quickly. Concerning cost expectations, the same association only sees room for 3% reduction annual because of high increase of raw materials such as steel and concrete. So now we will see some basic features on concentration photovoltaics. So in spite of its childhood, much less mature than CSP, there are already several megawatts installed around the world. The big cost reduction is still to come thanks to mass production. It doesn't need cooling water, except some special applications. It's a modular and scalable technology. So the basic strategy in CPV is substitution of expensive semiconductor material with a cheap optical system and low-cost mechanics. The photovoltaic cell is the best efficiency available in the market. So the graph shows how with 85% optical efficiency and 35% cell efficiency, which are the current efficiencies, we can reach 30% efficiency at module and 25% at system level. The advantages are less sensitivity to hot climates, a short time to operation, no water needs, and it's modular and scalable. Disadvantages: it's very sensitive to clouds. There is no easy storage ability, so these two issues should be solved, as TSO cannot accept sharp fluctuations in the generated power. Now we will focus on components. Cells, usually used triple junction cells. The principle is that each material operates at different wavelengths, so the three materials cover a large spectrum. The expectations on efficiency reach by 2009 40%, as today we are roughly 35%. Another fundamental component is the concentrator. So we have two main streams: lenses on the left and mirrors on the right. There is also another technology, which is central tower. This has been developed by Solar Systems in Australia. In general, the tracking system needs to be very precise, as the lead needs to be focused at the cell, not close to the cell. So the higher concentration ratio is, the lower angle tolerance we have. In practice, we have 0.1% accuracy. Structures need to be solid, and new structural concepts are being developed, as we can see on the bottom. What's the potential for cost reduction in CPV? if we see the graph on the right, the module accounts for flat PV technology accounts for 45% of cost. And then the 40% of remaining costs are proportional to area. So reduction in module cost and required area would lead to drastic decrease of levelized cost of energy. So for module, we have seen how the reduction can be reached by substituting cells by optics. Concerning the area, we provide here an example. So for the same surface, we can reach 50% more installed power. Or in other terms, to reach the same power, in concentration photovoltaics, there is need for 30% less materials and surface. The cost reduction expectations are as follows. Today, the cost of installed power is roughly between 6 and 7 euros per watt. It's expected in 10 years to be reduced by 3. So according to photovoltaic technology platform of European Union, we could find a levelized cost of energy currently about 30 cents per kilowatt hour. By 2015-2020, this cost could be reduced to 15 or 12 cents euro per kilowatt hour, and in 2030 6 cents per kilowatt hour, which means very good price, competitive with wholesale electricity. In terms of market growth, some companies provide their expectations. So, for instance, MCOR subscribed a contract to reach 200 to 700 megawatts in 5 years with some peak solar. Huascar Photon has in Spain several projects for some tens of megawatts. Sol3G, a manufacturer, expects to be producing by 2010 100 megawatt peak per year, with a cost of 1.72 euros per watt of module price. Then now we will finish with some ratios and comparisons. The power range for parabolic troughs is between 20 and 300 megawatts, for central tower between 20 and 100, for Stirling parabolic dish between 5 and 40 kilowatts. So small power, but this is scalable, so big power plants can be built on scale basis. This is quite similar to CPV, so each tracker has between 10 and 20 kilowatts, but this is scalable technology. Concerning operating temperature, it's about 400 degrees today for parabolic troughs, 600 for central tower, and Stirling parabolic dish can operate at 700 degrees. So efficiencies are proportional to these operating temperatures, 21%, 23% and 31% for Stirling parabolic dish. Concerning CPV, there is no notion of operating temperature, as it's a photovoltaic effect. So we will focus on efficiencies, and we see how today we are already at 25%, which is very good point, and very soon will be reached higher efficiencies higher than 30%, which is perfectly competitive related to thermal technologies. So as for commercial availability, parabolic troughs are definitely in the market. Central tower starts to be. Stirling, for the moment, there are only prototypes, but cost reduction is expected to come in the coming years, and then generation cost will be close to the other thermal technologies. CPV is also available right now, but in the coming years there will be a huge amount of megawatts available in the market. As for storage issues, on thermal technologies it's possible, at least for parabolic troughs and central tower. For Stirling parabolic dish it's open question, and for CPV there is no thermal storage, and electrical or other technology storage is to be analyzed, so for the moment no availability for storage. Hybrid design is possible for thermal technologies using any other fuel, not for CPV. As for water consumption, wet cooling tower takes a lot of big amounts of water, so parabolic troughs technology is about 6 cubic meter per megawatt hour. CPV and Stirling technology doesn't need water, so this is a big advantage. For land use in hectares per megawatt, for parabolic troughs it's needed between 2.5 and 3. There will be required more if it exists storage. This is 2 hectares per megawatt for Stirling and CPV. As for costs, investment cost of parabolic troughs is between 4 and 6 euro per watt according to storage sites. Central tower is something similar. Stirling parabolic dish is definitely much higher because we are only on prototype scale. CPV is between 6 and 7 euros per watt. So the levelized cost of energy today is about 260 euros per megawatt hour in South Europe, lower for Middle East and North Africa or any other sunny region. Central tower and Stirling technology, we don't have feedback enough from the field. CPV is roughly 300 euros per megawatt hour in South Europe, lower in sunnier locations. The expected cost of energy for the coming years is roughly 200 euros per megawatt hour in South Europe for parabolic troughs. For the other thermal technologies will be roughly in line with this. For CPV there is a big hope to reduce costs up to 120 or 150 euros per megawatt hour in South Europe and even lower in sunnier locations. So that's all. Here you can find some references. Thank you very much.